Hi folks, welcome to lecture number 4 in chapter 8 about the measurement of high voltages. This is our 34th lecture, and you remember in the last lecture, in the lecture number 3 of chapter 8, we were continuing with the peak voltage measurement, and one of the very old and traditional method of measurement of peak voltage was with the help of sphere gaps. As you can see in the slide, we talked about the sphere gap measurement, and let's we also learned that the consistently for a given gap distance and for a given dimensions of the sphere, you measure breakdown with a given voltage. For that voltage, it will work out to be every time the same. That is, there is a consistency in the breakdown voltage between the two spheres because they form a weakly non-uniform field. And when you set the gap distance in such a way that it is not greater than radius of the sphere, you get a linear characteristic in breakdown with increasing gap distance, and that quality was utilized. And of course there were better methods have come up lately, so this method is no more used, but you may find in every high voltage lab for some experimental purpose or other. So we talked about in detail. Now what happens? The breakdown voltage consistently would be measured at normal temperature and pressure. We call it NTP, normal temperature and pressure, because the temperature and the pressure actually determine the density of the air. This is all done in air. Now, I mean, as I said, people have, in this case, it is always done in air. So, normal temperature and pressure. Uh, so, if you don't measure at the same normal temperature and pressure as the charts, as the lists are, breakdown strength characteristic charts are derived, you may have to make a correction factor. I mean, when the temperature changes, the pressure changes, you may require to make a correction in the measured value. And as you can see it here, since in general, the actual air density during measurement differ from the reference conditions, that is normal temperature and pressure. Reference condition, you can imagine, the 20 degrees centigrade is considered to be the normal temperature and pressure of 1 atmospheric. So there is a requirement for correction factor. And then the breakdown voltage measured under other than the reference condition with which the charts are derived, you may have to get multiply the measured value by a correction factor to get the actual voltage. I mean, you don't know UB naught, as you see it here, are corresponds to the table values that being measured at NTP, and you want to know the UB, that is the breakdown voltage, and that is the voltage what you want to measure at other than the reference value. So you have to multiply it with a correction factor, KD. It is known as KD, as you could see it here. And KD is the correction factor related to the air density, delta. It has been given the air density, the relative air density RAD is given symbol of delta, and it is given by, as you can see, by this formula. P is the normal pressure pressure at the time of measurement. P is the time at the time of measurement, and P naught is the reference pressure, and multiplied by 273 plus T naught. T naught again as a reference temperature, up by 273 plus T. T is the actual temperature at which you are measuring. So it gives you a value T naught by P naught T, where P naught, as I mentioned, is air pressure for standard uh, condition, and P is the air pressure at the test condition at the time of measurement. And T naught is 20 degrees centigrade, and T is given in degrees centigrade. So this is how you can work out the correction factor, and which you must multiply with the value you get from the tables to get the correct value of UB. The correction factor KD given in the in table below, we will see the correction factor given in the table below has been worked out to be like this. And as you see here, the correction factor is almost equal to the relative air density. The two columns is, for example, 0.70, 0.72, 0.75, 0.77, and at the far end, 1.15 and 1.13. So these values are, the correction factor is almost equal to the relative air density of the air. We also talked about, in this case, that what are the disadvantages of measurement by this method. Yeah, for the measurement, every time you have to produce a breakdown, as you can see it, which is not desirable when you are measuring you want to measure only the voltage, but you have to create a breakdown. Only then you get the magnitude of the voltage. And that is why continuous measurement of voltage is not possible when you are increasing or you are decreasing the voltage. Continuous voltage measurement is not possible, and this method is not very accurate. There is a, in spite of all precautions and everything, there is an error to the tune of 3% estimated. So this is not very, when there were other methods were not there, this was being followed for ages, let me tell you. But nowadays it is not followed, since the better methods have arrived. So we'll finish with the measurement, with peak value measurement with sphere gap, because these can measure all types of voltages. Sphere gap, one advantage was it can measure AC, it can measure impulse, it can measure DC, all types of, and all polarities for all the types of voltage and polarities. There are tables for calibration table which are available in various standards if you want to refer. And that is why it was continued for a very long time for the measurement of peak value. It measures even AC power frequency, the peak value, because the breakdown always occurs at the peak value. In DC, an impulse of DC peak doesn't arise the question, but in impulse voltage, it is only the peak. So it is a very good method. In one way, it is a very good method, but having certain disadvantages. Yeah, next we'll go to electrostatic voltmeters. This I find a wonderful gadget. Let me tell you, this is a wonderful gadget. Again, some constraints and that is why not used very widely. But electrostatic voltmeters uh, have been built, as you can read here, the first point. Electrostatic voltmeters produced up to 1000 kV rated voltage are suitable for the measurement of AC power frequency or any other voltage having higher than power frequency at higher frequency, but it measures the RMS value of the voltage, and it can measure also the DC voltage. Obviously, it cannot measure the impulse voltage because there only the peak voltage is measured, but this particular electrostatic voltmeters are designed on the principle where it can measure only the RMS values. So RMS value of sinusoidal any frequency voltage and also DC voltages. Yeah, as for high voltage range, contact compact voltmeters with SF6 gas, and I mean instead of using air, I'll show you first the picture. This is an electrostatic voltmeter. What do you see here? There are two plates on the right and the left. On the right is the high voltage electrode, and this is a parallel plate electrode system with the plates given a particular shape at the brims. And we have learned what kind of field will be given rise in this particular case, a uniform field. So we try to produce a uniform field between two parallel plate electrodes. The right one is the high voltage electrode and left one is the grounded electrode, and grounded and also movable electrode. This is not just grounded, this is also movable electrode, and this is fixed. This one is fixed electrode, which is given the high voltage. Movable electrode means when you measure in a wide range the voltage, you may have to set the designed gap distance between the two electrodes. So the grounded electrode is movable and it is fixed for the desired range of the voltage measurement. It may have to be changed. I mean, you can imagine this can measure a few hundred volts to more than 1000 kV. Imagine few hundred volts to more than 1000 kV. So you have to set the gap distance between the two plates. We have to differently. I mean, you have to vary the gap distance for the range of measurement. Now, for the construction, when we are looking at the diagram, is that in the grounded electrode, movable and grounded electrode, in the center there is a enlarged. There is a what do you call it? To be an opening. I mean, in the center there is a small disc taken away, cut in the flat plate electrode. In the center, the plate is cut and replaced with that circular portion is cut away, and it is replaced with some mechanism for the measurement. As you can see it here, we'll go back to, yeah, as you see it here, the these voltmeters were, yeah, let's talk about a little bit about history of the voltmeters, were suggested by Kelvin in 1884. something like 135 years ago. So, and for the measurement of RMS value of power frequency voltage, they are developed to follow the Coulombs Law. As you know, Coulombs Law, you must have learned right in the field theory, which defines the static electric field as a field of force, the static electric field between two electrodes. And a force is developed, and a field of force is developed between the two parallel plate electrodes. As you have seen here, the two parallel plates, there is a field of force developed between the two. Then the field produced between two parallel plate electrodes with shaped profile brims, as we discussed, is a uniform field. We try to produce a uniform field when we take very large size of the plates, at least towards the center of the plates, the effect of ends is minimized and you would get a uniform field towards the center. So you may have to take very large electrode system to get the field developed in the towards the center of the plates to be uniform, actually uniform, no D-shaping of the field. You know, when the field is not uniform, when you plot the squares between the equipotential and current flow or the field lines, they must make perfect square. When they make perfect square, you can you can take it for granted that the field is uniform and that you do get towards the center that we dealt right in the beginning of this course. If the voltage applied across these parallel plates having a gap distance, let's say x, it has been taken to be here, capital X. So don't worry about it. We have deliberately not taken D as the gap distance because we need D for differentiation also. Then the uniform field produced in the gap between them will have an intensity E, electric field intensity E equal to U by X. This is the case in all uniform field. U by D we have learned earlier, isn't it? U by D, in case the electric field intensity in uniform field is U by D, the voltage applied between the two electrodes divided by the gap distance. So this will be U by X in this case, as we can conclude. And the attracting force F between the two plates on an area A, if the area of the plates is taken to be A of the electrodes, is equal to the rate of change of stored electrical energy, WEL. W is the energy and EL is electrical. So the rate of change of stored electrical energy, WEL, the force will depend upon WEL, or per unit distance, in the capacitance formed between the plates. So obviously, when between the two plates, whatever dielectric you put, it will form a capacitance. It was being practiced for air as a dielectric earlier, but the sophisticated electrostatic voltmeters produced, as I mentioned, up to 1000 kV, people have been using air, compressed air, or SF6 gas, or even vacuum. If you use SF6 gas and vacuum, you can imagine you can make the size of the total electrostatic voltmeter, that means that of the plate and everything, very compact, because the breakdown strength of SF6 gas is 3 times that of air, and vacuum is even of something like 5 times that of air. So people have replaced the air with SF6 gas and vacuum in between as a dielectric. This is the dielectric, and as I mentioned, it is here. Yeah, as you see here, this is a very simple arrangement, but size of the uh, um, plates may be very required to be very large. And yeah, yeah, this is what, yeah, let me explain. A cut made in the, a cut, just a minute, annular cut. The cut is made to be annular uh, in the uh, ground electrode. Hmm? In the ground electrode, annular cut is made. And it was mentioned, I just want to show it to you. It was mentioned in some of the slides. Anyway, doesn't matter. As you see it here, this is from here, this position to this position, an annular cut has been made, and this is an enlarged view of the proportionately enlarged view of the circular cut or annular cut portion. This is an enlarged view of the annular cut. This is actually behind there. There is a kind of a floating mechanism. As you see it here, this is a kind of a floating mechanism. This floating mechanism uh, experiences the force, and because of the electrostatic force between the two plates, depending upon the magnitude of the voltage, this rotates, and by rotation it rotates the deflection of the mirror. As you can see it here, this is the deflection. This is a mirror which deflects, and the how much it deflects depends upon the force. And there is a mechanism of fixed light source is fixed. It is reflected on the mirror, and because of the reflection, the the reflected light wave falls on the fixed scale. That's on the leftmost side is the fixed scale. So the because of the force experienced by the floating mechanism accompanied with a mirror, the mirror rotates or twists, and the fixed light source falling on the mirror, it gives different reflection angle on the fixed scale. And there you can read the fixed scale is calibrated according to the range set, that is the gap distance range set between the two plates. Different different calibration in the fixed scale would be there. I mean, the scale will have to be changed according to the range you select for the measurement, and that will directly, the light will fall on the magnitude of the voltage desired to be measured. So it's in one way, it's a very simple arrangement, but it uh, only problem is that the size is quite big. You need, for example, we have learned in case of capacitive voltage divider, you need such big, large, huge capacitor also for the measurement of peak voltage. So that can be replaced by this. Only constraint here once again is that it cannot measure the peak voltage, it can measure only the RMS value. So this mechanism cannot be used for the measurement of impulse voltages. So let's derive a bit of theory. As you can appreciate, the force between the plates is negative of del WEL, the energy, and by del X. And when you do it further, that is the energy stored is in the capacitor, that is half Cu square, as you can see it here. And in the case of the uh, uniform field form, uniform field capacitor, this equation can be derived in such a way, having the plate area to be A and the gap distance X, and epsilon naught will come, only epsilon naught will come into picture, even when you take vacuum or a subscript gas, because relative permittivity in that case can be taken to be 1. So this derives the equation, that is the force, the magnitude of the force, as you can see it here, is equal to half epsilon naught u square A by x square. So x square is the fixed gap distance according to the range, isn't it? Is the as you see here, epsilon is the permittivity of the insulating medium, and x is the gap distance between the parallel plates electrode having area A. The X is chosen for the required range of measurement. So X is also, you can say, is fixed. So the force is proportional to U square, and this gives you the this gives you here the mean value. It measures the mean value of the voltage being applied. So the mean value of the force is used to measure the RMS value of the voltage, because you are doing the theoretical calculation here to determine the mean value of the force of the, and that will depend upon the RMS value of the voltage. So when you measure over a range, you can say, when you measure when t is a proper integration time, t is the, that is one cycle, that would be taken to be one cycle integration time. So this works out to be equal to epsilon a by 2x u r RMS square. So this A is fixed, X is fixed, epsilon naught is fixed. It is the proportional to the square of the RMS value. The indicating instrument uh, uh, show F at fixed and X is then proportional to the RMS value. Actually, X is taken to be fixed. The indicating instrument, the force, let's go back. Yeah, the force D or X is fixed for the range, and the scale here is calibrated according to the range. Already you put the scale according to the range fixed, and then the force reflects the mirror, the floating mechanism. This is a, in the center, as you see, is a floating mechanism, and the floating mechanism rotates according to the magnitude of force experienced by that mechanism, and that reflects the light from the fixed source, reflects the magnitude of the voltage directly on the scale chosen. So there may be different ranges, I mean 3-4 ranges, for that means the gap distance to be set in a different different magnitude, For each range, different magnitude of gap distance will be chosen, and for each gap distance chosen, there will be a calibrated scale. So that reads the voltage directly. I hope you are able to understand. I have tried to explain it to the best of my ability out here. Now, this is a wonderful thing, as you see here, a sectional view of 1000 kV electrostatic voltmeter with dimensions, as you see here. This much is showing you 1 meter. So how many meters high would it be? 1000 kV. 3, 4, 5, 6, at least 6 meters. This would be something like 20 feet high, at least 20 feet high. 1000 kV electrostatic voltmeter would be something like uh, 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 20 feet, more than 20 feet. As you can see here, these are insulating cylinders. Then 600 kV capacitor tube is there, 600 kV air and disc. Then these are the different components, 600 kV gap disc, then stress control cylinder will be needed. At such high voltages, you have to control the electric stress other than wherever the voltage is going. So high voltage measuring electrode, this is showing, and then measuring disk of guard plate. Then we have uh, yeah, uh, weighing balance is there. Yeah, when there is any movement, it must be counterpart should be there to balance the movement. That means, as we saw, there is a floating mechanism which experiences the flow, the force, and rotates. So there must be a counter uh, arrangement mechanism to check the movement. Otherwise, it will go straight. It will go very unlimited movement. It will go. So there has to be a counter to check the movement. There has to be a counter movement mechanism, and yeah, this is the whole tank as it is there, and gap adjustment can also be done for different range. So this is the cross-sectional view as you can see it here. Mm, These are electrodes for provided here so that electric stress is controlled over there. So this is a very elaborate arrangement, but very accurate. Yeah, the best part of it is that electrostatic voltmeters are very elaborate. Only the drawback is you see. Yeah, let's talk about that. Yeah, the we can discuss these points have been sorted out for you for the arrangement for the electrostatic voltmeters. The electrostatic voltmeters are arranged such that one of the electrodes or a part of it is allowed to move. As I mentioned, normally the high voltage electrode is fixed and the ground electrode can move to set the gap distance between the two plates for the desired range of measurement of the magnitude of the voltage. Thus, electrostatic voltmeters are RMS indicating, as the from the theoretical we have derived, the mean value has been calculated. The force is would depend upon the mean magnitude of the voltage. RMS indicating instrument, if the force integration and its display follows the equation, what we have seen the equation. Then various voltmeters develop differ in the uh, various voltmeters developed. Yeah, sorry. Various voltmeters developed differ in their use of different methods of restoring force. Yeah, as I said, the floating mechanism which experiences the float, there has to be a restoring force mechanism accompanied with the floating mechanism. And it is required to balance the electrostatic attraction. Then it becomes very delicate instrument then. And there is a floating mechanism which should not twist beyond a certain limit. When it is being transported, it must be taken care that it doesn't get exposition, doesn't get disturbed. So this is in huge, robust. This is not huge. This is a huge instrument, but not very robust because the because of the floating arrangement of the floating mechanism, which actually reads the magnitude of the voltage. This can be achieved by suspension, the counter or restoring force. It can be achieved by suspension of the moving electrode on one arm of a balance, or its suspension on a spring, or the use of pendulous tensional suspension. I mean, this is all mechanical arrangement. Basically, mechanical suspensional suspension, tensional suspension. Tensional means from the tension suspension, which has a counter mechanism, you can say. The small movement is generally transmitted and amplified by a spotlight, as you saw it, and mirror system, but many other systems have also been in use. The electrostatic measuring device can be used for absolute voltage measurement, since absolute, when I said RMS voltage measurement, since the calibration can be made in terms of functional fundamental quantities of the gap length and forces. Then yeah, for a constant electrode separation distance, that is X, capital X has been taken here, the integrated forces increase with proportion to RMS voltage square, U RMS square. The integrated forces increase proportional to the square of the RMS voltage, you can say. And thus, the sensitivity of the system for low voltages or low range of voltages of the rated voltage of the instrument is small. You can imagine that it is being mentioned. Let's draw a line here. Yeah, let's draw a line here. Below here are the disadvantages written here, and the measurement of voltages lower than 50 volts is not possible, as you see it here. Measurement of voltage lower than 50 volts is not possible here because uh, the force becomes too small to cause a rotation in the floating mechanism, that is the mirror would not rotate. So this is the minimum voltage to be measured is more than 50, say 100. But still, suppose you are able to measure from 100 volt to 1000 kV, it's a very, very wide range. Then the other disadvantage is that uh, is uh, uh, by yeah, I mean the range problem has been overcome. The disadvantage I mentioned here that the you can by varying the gap length in appropriate steps. The gap length between the two plates can be varied in appropriate steps. Well, I can imagine in a compact like electrostatic voltmeter, the range may suffer more. So it may be used only for example, 1000 kV. So the minimum voltage measured may be not in hundreds, maybe in few kV. Hmm? And the high pressure gas or even vacuum between the electrodes provide very high resistivity, therefore low active power loss. Active power loss is always a concern, and in any capacitor formed by vacuum or gas, the active power losses are very, very small. And when you have high pressure gas or vacuum being used, the active power loss decrease furthermore. Then the load inductance and electrode system capacitance, however, form a series resonant circuit which must be damped and thus limiting the frequency range. And this is a problem, the last one mentioned here, is specifically in case you are measuring high frequency voltage, which is rare. High frequency voltage measurement requirement itself may be rare, but it is equipped to measure that also. But the problems arises at high frequency that the load inductance and the electrode system capacitance value, that is XL and XC, the inductive and capacitive reactances acquire different values. The inductive reactance increases, the capacitive reactance also increases. Uh, so that at high frequency, so that must be taken care of, at high frequency. So that gives some kind of a requirement for a damped circuit. Uh, you need to damp the circuit to avoid the resonance, you can say. And that has to be estimated when, at what frequency it would uh, happen for a particular load, for a particular instrument. So this is how the electrostatic voltmeters work and are being in use. And modern electrostatic voltmeters have been constructed with SF6 gas and vacuum, use dielectric instead of air, simply air. I have come across electrostatic voltmeters working simply in air, but the size of the electrostatic voltmeter is large, and you have to change the range, and the sensitivity is there of the reflection of the mirror on the uh, calibrated scale, etc. So all these things, once again, have not promoted the use of electrostatic voltmeters very widely, although it's a very nice uh, uh, and accurate power frequency, measurement of power frequency, voltage, and RMS value, RMS value of power frequency voltage, and also of high frequency voltage, and also DC voltages. So, yeah, this is you can read the summary what we have dealt in this chapter number 4. Uh, that we have been talking about the measurement of high test voltages requires entirely different techniques as compared to the measurement of power frequency voltage in power system. So special techniques we have learned in this chapter for the measurement of high test voltages of all the kinds, AC, DC, impulse of all the both the polarities, etc. And we can conclude the best method is nothing but a potential divider, and there is a half dozen types of potential dividers. Potential dividers given rise so that the cost of the instrument is reduced as far as possible, cost, size, etc. And yet you have flexibility in measurement of continuous voltage in case of AC and DC, and a good measurement of impulse voltages also, and to be able to measure the very fast impulse voltage, that is lightning, then the slower impulse voltage of switching of either polarity. All arrangements are there, and best is to measure with the help of potential dividers. I mean, there are so many types of potential dividers, they make their suitable application. Sphere gap is dying. Measurement with the sphere gaps is dying, but sphere gaps become like an ornament in any high voltage lab. Even in my high voltage lab in IIT Kanpur, we have a sphere gap available. We do use it for different purpose, for demonstration, for even measurement on very long gap in weakly non-uniform field. It can always be used. It's a classic instrument, you can say, arrangement, or classic arrangement of two spheres between each other. So uh, next we will go to the quality control of the dielectric. We have learned the measurement of high voltages, and how can we check the quality of finish of the dielectric on an apparatus. That we will go in the 9th chapter. So I thank you very much. Here I have earlier also given you the reference books are there, the latest books published in 2019 of ours, and this book is published in India. The second book is published in US, and the third in 1995 was published again in India. The latest book takes care of the whatever I've been teaching to you here in this course with these lectures. It is all there in our latest books. You may refer it to. So thank you very much, and let's make a day, and